triangles. Clemson's campus is real uptight compared to a lot of those. Oh yeah. Look on the website, man. We're known as a jock school. A lot of people don't like that.
Oh, I totally believe it. I mean, I'm a fat guy surrounded by people who have
There's a guy. Did
Yeah.
Cooper come around to you guys? He was talking about a guy in our building. His roommate dropped out because he didn't want to walk everywhere. He was like, I'm just gonna quit college because
I can't walk.
Like, I know, like, I felt really bad.
Like, I'm about to get a skateboard because of all these hills. Like, for real, I want to get one of those long boards. It was like, it's $100. The wheels cost like $50, and I was like, bump it. I'm getting a long board. Those things are fun. I was going down there. I'm not going to go down that huge show by that badly. I'm going to die, but I'm going to have a little bit of fun with that.
I got my long board.
How much you got it for?
Probably a total of about $250, $300.
You ever wiped out on one of those?
All you really do is, lean. You gotta keep your center balance right.
It's just a little easier than a skateboard because you don't have to like literally pick it up and like move it each time you're trying to think. You just balance it left and right in there.
Have you ever wiped out on one of those?
Yes, it was on my skateboard.
Pretty nasty.
Because I had two really nice skateboards and one
the guy coming
they split in half. I wiped out so hard, but I skinned literally the entire front of my body.
Yeah, I've seen that happen. There was a guy coming down. It was out by Bowman Field, which is not particularly steep. It's pretty steep on the far side there. He wiped out at the bottom of that. Sliding on the concrete.
It's not fun, especially when your board's $500 and it's split in half.
I wasn't worried about the board.
I was after I healed.
All the work on my shoes. I don't want to mess with my shoes.
Okay, we got a couple of people haven't shown up yet. Let's see. So, but I think it's time to start. Okay, let's see. Homework that I've returned. You'll notice just about everybody. I wanted to give you a redo on the dimensional analysis stuff. It's not very much, but I just want to make sure everybody understands what that was about because you're going to use it a lot. And so please study the solution. I'm not saying that there's anything that, it's all in the solution. I want to reiterate what I wrote in the solution for you. So, oops, no, 10. There we go. Okay, so for example, let's suppose we have a triangle with three sides. So there are two basic types, L and T, that you're going to be concerned with so far. When we get to chapter 3, there will be a third type that we will introduce. But for now, there's just two. So everything that we're going to be concerned with at this point will be some combination of L and T, and L may be raised to some power and T might be raised to some power. So for example, the sides of a triangle are all lengths, right? So, and be careful of the notation here. The square brackets go around the variable that is under question. What is A? What is the type of A? So read this as the type of A. Mr. Flanagan. There you go. The type of A is L. It's a length. That's all this means, right? And B has the same type, and C has the same type. They're all lengths. Okay. So that's what I'm looking for here. It's going to get more elaborate as we go through this, but that's what I'm looking for at this point. So an area, like the area of this triangle. Let's suppose we're looking at the area. The area of the triangle will have dimensionality or type L squared. Because again, you're making everything out of the basic types of length and time. And that's all there is. So if something is moving, let's suppose we have a marker here and we have a body whose distance is measured here, let's call it x, and x is changing in time, could be changing in time. The dimensionality of x is a length, right? That's basically what it is. And we could construct a velocity, a speed, would be, for example, some kind of distance over a time. We're going to talk more about how to construct speed, but some kind of distance over a time. And the dimensionality of that then will be length per time, or L over T, if you like. Okay? An acceleration would be a change of velocity over time, so an acceleration like that. That's what I'm looking for. So please go back and redo that homework. An aspect ratio of a rectangle, which is the let's add another page, an aspect ratio of a triangle of a square is just the ratio of length to width. And so the aspect ratio is the ratio of two lengths, and so this is dimensionless, right? So another way of understanding this is if you change your system of units, the aspect, if you're changing from, say, I'm changing from measuring distances in centimeters, I'm going to start measuring it in meters. And so I want to convert all my previous measurements. The aspect ratio doesn't depend on the system of units, right? It's going to be 2 to 1 or 3 to 1 or something. So that doesn't depend on whether you're measuring distances in centimeters or meters. So angles are dimensionless, and please remember to use angles in radians, not degrees. There's a reason for that, which you will come to understand as we go through this. Okay, any questions about the dimensional analysis? Yes, sir.
On the slide before this, you had one other one that I didn't get. It was
Good.
LT to the -2. What is that?
Yeah, that's the speed, length per time. Oh, I'm sorry, length per time squared, an acceleration. So if you don't understand acceleration at this point, that's all right, but it's a change of speed. So if you're in a car, you're accelerating from rest, how much speed did you gain over how much time? That's an acceleration. And so that's going to involve a length and then a per time. Same thing if I take a body and drop it, because of the force of gravity, it's going to accelerate downward. And that acceleration can be expressed, the rate of acceleration can be expressed as a velocity per time, or in other words, a length per time. Okay. All of the physical things that we're going to be talking about, all things that are measurable or related to measurements, things that have physical significance, are going to be length to some power times to some power, a product of those two things. Okay. And then when we get to chapter 3, we'll introduce a third type, and when we get to next semester, we'll introduce a fourth type. So there are these other types like charge and mass that are coming, right? But so far, we're not concerned with those. So far, we're concerned only with length and time. Okay, so please, everybody, redo your dimensional analysis. It should only take you a couple of minutes, but I just want it ingrained. Mr. Jackson.
I was going to say, did you want us to turn them in?
Yeah, please. Let me see them again. Go ahead and redo them and let me see them. Seems like there is something else I was going to do. I can't remember what it was. Okay. Yeah, please. So, chapter 2. Any thoughts about why chapter 2 is on the topic that it is? Why in the book on physics, after we talk about general principles, what's the next subject in logical progression? Vectors and calculus, more generally, math. So why? Why is math next? You might think, well, why don't we get on with the business of physics? Why is math Mr. Flanagan?
It's abstracting away all the properties
All the what properties? Yeah, the base property. Exactly, there it is. So it's abstracting the base property, which is quantity. So math is the study of quantity. In fact, math originates then with the physical. It's an abstraction based on the physical. So he has begun here for you this process of abstraction and going back to the concrete. So he's going to, throughout these books, this is one thing that I really like about, there are many things I like about this textbook. There's one thing he's very careful to spell out for you. He's going to go up and down this ladder from the concrete to the abstract and back. So a concrete would be a square object. An abstraction would be the shape of the object, okay, or the length of the object, right? So he's going to go back and forth, abstract to concrete. So the first abstraction we make is quantity. We're just going to study quantity as quantity. Get rid of all the other attributes of the thing, whether it's alive or not, whether it has any other qualities, independent of time. Let's just abstract out quantity and deal with quantity as quantity. That's math. So notice math comes from the physical. Math is not something that's invented by the human mind just out like the dew fall, comes down and it's just there. It comes from living in the world and It's a natural process for the human mind to form abstractions from the concrete experiences that we have. But we don't always live up here. We want to go back and say, well, let's get back to the concrete. That's the process. So we're going to do this, but then we're going to come back down and pull something more. So we're going to go up and down this ladder. So this is the first time we've done that in this. And so the process of abstraction then, please remind me, what is abstraction? Yes, sir.
Removing all the other aspects of the thing.
Right, considering some aspect of a physical thing as though it could exist on its own. So quantity exists only as a quantity of something, but we're going to consider quantity abstractly as though it could exist on its own, whereas quantity doesn't exist outside the mind, except as a quantity of something. So what is a being of reason? You're encountering that in your reading, Mr. Jackson.
Something that only exists in your mind, I suppose?
Right. Something that exists only in the mind. The wording is a little funny. Being a reason, you might think, well, that's a person, right? A person reasons. A person is a being. So no, that's not what it means. A being of reason is a thing that exists only in the mind. Can you give me an example of a being of reason?
An infinite plane.
An infinite plane. Infinity, speaking generally, is a being of reason. Infinity is a being of reason. What else is a being of reason?
Concept of nothing?
Nothing. Yeah. Does nothing exist? No. No. What is nothing?
Lack of something.
Sorry?
A lack of something.
It's a lack. And so, in fact, nothing cannot exist. Right? It's the being of reason. It exists only in the mind, and what we think of it is it is an understanding of an absence or privation, something that should be there that's not. So, a person who's blind should have vision, but blindness is then an absence of something that should be there. So it's a privation. The blindness is not a real existence. The blindness is an absence of vision. So the blindness is not really anything. We speak of it in those terms, though, as though it were something, and that's an indication that it's a being a reason. It's something that exists only in the mind. What exists in the person is, two people. One, the normal situation is to have vision. The other, and obviously this person doesn't, so there's something missing. Right? Okay, so that's a being of reason. All right, so let's go back a little bit to what is the basic concept of vector. So here is something that's very simple, again, drawn from common experience. What is the basic concept of vector? And I'm looking here on page 39 of the book. I've got to remind myself exactly what his wording here is. His basic concept of vector. What is it? Somebody remember, please. Basic concept of vector. It's one of your questions.
Something with magnitude at first?
Yeah, not magnitude at first. Right. Hold on to that thought. There's a difference here, Mr. Kelly. Length. Why the difference between length and magnitude? What's the difference between length and magnitude?
Well, length is regarded as its just quantitative extension, whereas
Exactly.
magnitude would be like a qualitative analogy.
Excellent. Excellent. Length is quantity. Magnitude is a generalization of that to include qualities. So there could be even, somehow, generally we're going to be speaking about vectors in relation to qualities, not just quantities, but the fundamental definition, the fundamental concept of vector comes from length. So how do I get to Greenville? Go 30 miles east? Something like that. 30 miles east, right? That's a vector. That's basic idea of a vector, displacement from here to there. There is an orientation, so there's a from and a to, so there's a sense in which one end is the tail and the other end is the head. And we draw it as an arrow, put an arrow on that end, and tail feathers over here or something, so we know it's that away. So other examples of vectors, really simple, right? Again, the basic concept using length. Displacement is a real obvious one. How about maybe that's just such a primitive one. Yes, ma'am.
The
Yeah, now velocity is now a combination, isn't it? So it's not exactly quantity specifically, because to measure the velocity of something, I have to measure a change. And change is not a property. So how do I measure change of place? I have to make two measurements. Remember in the appendix we were talking about, in order to measure change, I have to do two measurements, not one. In order to measure change of place, I have to make two measurements. But the velocity's also got this concept of time involved in it, so it's a little bit more mixed, but it's certainly easy to generalize from the understanding of, go east 30 miles. Well, do it in an hour, right? That's kind of like a velocity. So it's adding a little bit more. So it's a little bit more than simple quantity. That's not bad. Okay, so then he goes down to, a basic question. Is quality essentially reducible to quantity? Now, please explain why. The key word being essence.
When I got it wrong on the homework, you said that color isn't a shape or a number.
Right.
So, it can have an intensity, but it's not like just a number.
If you want to explain in essence what red is, you're not going to use a number to explain redness to somebody in essence. You want to explain what is the essence, you wouldn't use just a number or shape to explain color. Okay, let's see. Okay, so that touches on something. That's right. I wanted to briefly discuss this, and Mr. Vestal had this question about on the homework last time. Is substance measurable? So there was a question: can you measure substance? And I wanted to discuss this briefly. So substance is not directly discernible by the senses. You don't see the essence of a thing by looking at it. You don't see what that thing is directly. You see colors and shapes, and you may smell it, taste it, touch it, textures, hardness, and other things. Maybe using your senses will reveal to you what the thing is. But the thing it is not directly visible to your senses. So I look at a person, and I don't have a sense. None of my senses tell me, person. I have vision and hearing and other senses that I can use to determine that that's a person. But I don't have a sense that directly reveals to me that it's a person. So substance is not directly knowable through the senses. It's something that the intellect has to come to a conclusion about based on the evidence. But again, the only evidence we have is the senses. But the sense is not, we don't have a sense meter that tells us person or gold or water or something like that. So substance is not directly revealed to us. It's not a property. It's what something is, substance. And as a result of being what it is, it now has properties, and we can see them. And so we can work back through our senses. I can look at it, I can do things to it, drop it, and stomp on it, and do things to it, and see what it is. But that's something, a process I have to go through. Okay. So that's why substance is not directly measurable. It's not something that, it's something because it's not a property. Properties are directly sensible and therefore may be measurable, but substance is not one of those things. Okay, good. I'm sorry to digress a little bit. I should have done that right up at the beginning. Okay, so now given that the basic concept of vector is length and direction, now what does that do to extend to our basic understanding of length? Well, it adds direction. Now we have something new. Before I was just talking about the length of the table. Well, now I'm going to add something new. I'm going to give you a direction, east. What are other examples of direction? Just pure direction. Up, down, left, right, forward, backwards, north, south, right, basically. Those are pure directions. They're not lengths. What category might they fit into? Orientation. Good. Thank you. Right. Orientation. It's an orientation, right? East, north, south. I'm facing up. I'm facing down. I'm facing that way. I'm going to walk backwards. Those are kind of orientations, directions. So I would put direction in that kind of category. But it's obviously directly related to quantity in a sense, because if I go that way or if I go that way, I'm doing something different, right? I end up in a different place. So it's obviously related to quantity in that sense. Okay, so what is the formal definition of vector? That's on page 42. Okay, I'm going to start calling on those who haven't yet answered. Miss Barber, what is the formal definition of vector?
It says it's a mathematical entity of a given magnitude and direction.
Right, now he's generalized. It's a magnitude and direction. Magnitude is a generalization of lengths. So magnitude of the vector, we talk about the magnitude of the vector, but it could be something, for example, velocity is an example. If I say I'm going east at 30 miles an hour, the magnitude of that is the speed, 30 miles an hour. That's not a length, it's a combination of things now. But the direction is still just east. So now I've generalized this. I've extended the idea to include things other than just quantity. Okay, do you see how simple that is? Really a very simple thing. And he really does want you to see it as a simple thing. He's not trying to belabor it in order to make it complicated somehow. He wants you to see these really are simple things, that we should have kind of common sense connection to these sorts of things. And we're just going to build on this common sense. Okay, so a nice object that has vector-like properties, a physical object that corresponds to the abstract mathematical idea of vector, is an arrow. So it has a tail and a head. That has a length and a direction. So you can think of it as an arrow, but it's fundamentally not exactly an arrow, right? Okay.
So do all magnitudes represent an intensity? Like a qualitative intensity? Or they measure an intensity?
I'm not sure that I can. I'm not sure I can give you a blanket yes on that. Certainly, a lot of things I think of are intensities of qualities. Yeah, as you know, what is not a quantity, but can be represented as a generalized vector. I can think of qualities, but I'm not going to be able to say, yeah, that's the only thing that you'll encounter. So, okay, so how about a unit vector? What is then a unit vector? Let's see. Continue, Mr. Covington. How about unit vector? What is a unit vector?
It's a vector with unit length and a specified direction.
Right, very good. So it's a generalization of the understanding of unit length.
Yeah.
We're adding direction. So a unit vector is something that adds to the concept of unit length, now concept of direction, combined with it. So a unit vector is going to be expressed as a symbol. Okay, so now we haven't talked about it much. Actually, let me do it this way. Okay, so some notation. Vectors are indicated by an arrow on top. So this is a vector A, which means that it's a combination of magnitude and direction. So there's something we call a magnitude and something called a direction. Now, one way to write this is this. So what is the meaning on the right-hand side? Here's a vector. What are these things on the right-hand side? Another way to write this would be like this, which might be an easier way to start thinking about it. What is the meaning of this?
The length of it.
Bracket, yes, the magnitude of it, right? Magnitude of A. If A is a distance, then it's a quantity. It's a length associated with that vector. Okay, so Mr. Disharoon, what does this mean with a little hat on top?
Direction.
Yeah, that's the unit vector. It's not just direction; it's the unit vector. So it has in the direction of A, but whose length is only 1 in that direction. Right. So we're gonna extend that direction in the so that's the direction, and here's the magnitude. So we're going to combine the magnitude and the direction in this fashion. So now that combines to form the vector. So this is another way of writing it. And A without the arrow, without the bracket, the vertical lines on either side, just A would also stand for the length of A, or the magnitude of A. So magnitude of A, sometimes written just A. Just take the arrow off the top and call that the magnitude of A. Okay. How many, so we can use unit vectors to combine. And just, in fact, let's talk about adding vectors, summing vectors, vector addition. And now if we go back to the fundamental idea of a vector as, for example, a displacement, what is the physical meaning of addition? If I take two vectors, each of which is a displacement, and then I add them, what does that mean?
Just combined displacement.
Yeah, successive displacement. So if I consider these vectors as displacements, then a vector addition is the same thing as doing successive displacement, one upon the other. So if A is this vector, so it has some magnitude and a direction, and B is this vector, then the sum of those two is simply A plus B. Okay. Now notice that this means the magnitude of A plus B. Is that going to be equal to the magnitude of A plus the magnitude of B? Not usually. Why, Mr. Vesta?
Because it's a triangle.
Right, yeah. The hypotenuse is not equal to the sum of the sides, and well, that would be true for a right triangle, but so in a general triangle, the third leg is not equal to the sum of the two sides, generally speaking, only if they're parallel to each other, in which case it's collapsed. It's not a triangle, it's collapsed down. You have two, A and B are both in the same direction, and in that case, A plus B would be equal in magnitude to the two individual magnitudes added together. Generally speaking, not. In fact, what if A and B are in opposite directions, so we have A and B, then the sum could be 0 if B is the opposite of A. So what does this mean? What does that thing mean?
B is the same as A, but going the other direction.
Exactly. Yes, sir. Same magnitude, but their directions are opposite, opposing each other. So the little negative sign is an indication of direction. So what does it mean if I say I'm going to take 2 steps forward? All right, that's obvious enough. What if I say I'm going to take negative 2 steps forward? I don't really take negative 2 steps. Negative 2 is not possible, right? I can't take a negative 2 steps. I'm taking 2 steps just in the opposite direction. Opposite to forward is backward. Okay. So the negative sign indicates there that the magnitude isn't negative. It's an indicator of that. It's a sign. The sign is an indicator that the direction is opposite, not that the magnitude is opposite. Is that clear? Okay. So in general, this is not equal to each other. These two. Okay. And how about difference then? How would I express the difference if I have the sum of two vectors? Now, how would I express the difference? What does that mean? Sum is successive displacements. Mr. Fanning, would you like to try that? What would you think about the difference between two vectors?
How far the 2 points are from each other?
Yeah, exactly. So I give 2 sets of directions. Go to east 30 miles. And then I give another set of directions. Go north 30 miles. Well, the difference tells you, well, how far are you apart from these two endpoints? That's the difference. How far do the endpoints, can you express that? So here's A, and then here's B. Now notice there is a sign to this. There's an orientation, A minus B. Okay. Notice that the head of this arrow here is in the direction of the one that's first here. And the tail of this is in the one that's second in this difference. Another way of saying that is, let's take the opposite of B. Let's see here. Let me draw it up here a little bit. So I have A, and now I'm going to add to that the negative of B. This is negative B, right? It's same length, but in the opposite direction of B. And now I'm going to add these two vectors. And then this is A plus the negative of B, which is the same thing as A minus B. Is that okay? Okay, so now I'm going to make use of these addition properties. What we're doing here is developing an algebra associated with vectors. We have algebra for numbers, which is what you're used to dealing with. You have a symbol that represents a number, and maybe a symbol that represents another number, x and y, unknown numbers. And you start writing algebraic expressions, solving quadratic equations, things like that, involving symbols. So we're going to do the same thing now. We're going to develop vector addition and subtraction. The next thing that's coming is vector multiplication. That's coming. We're going to do a lot of things with vectors. So we're developing vector algebra. Because these things are physical, you can start doing things like adding and subtracting displacements, things like that. Okay. So now let's combine the idea of unit vectors along with vector addition. So I could set up on a plane like this in 2 dimensions 2 different unit vectors. I'm going to call one x hat and the other y hat. And from the origin of this system, I can represent any point out here in terms of successive displacements from the origin. So how many steps in the x direction plus how many steps in the y direction will get me to that vector p. So this is p, the place. So I could write p as being some number of steps in the x direction, some number of steps in the y direction. And then that will describe any point on the plane. I can get to any point on the plane. So this is called a Cartesian coordinate system. Why Cartesian? Does anybody know? That might not have been in Descartes, after René Descartes again. And we'll talk more about Descartes' contribution in this chapter. But for now, just note that he's credited with this idea that every point on the plane is going to be given a pair of numbers. So, and not just a pair of numbers, but you also have to specify the directions, the unit directions. So first he lays out these 2 unit vectors. Now they're mutually perpendicular. They are perpendicular to each other. Any thought about why that should be? Why, so for example, on a map we might think of east and north. But why not give coordinates for a map in terms of east and northeast? Why should north and east be separate, Mr. Flank?
Because when you're dealing with like sine and cosine for angles, you want 90-degree angles.
Yeah. Okay. That's good. There's a more fundamental reason. Let's see, Mr. Dishwood.
Because you need to make more directions, and 4 is like the least amount, so you can cover all directions.
Yeah. So you can cover all directions. So think about east. Now, if you want a second unit vector, don't you need one that's in some sense completely independent of east? And what is independent of east? North is completely independent of east or south, either one. Okay, but you could take a pair, east and north, or south and east, or any pair. Could be north, east, and northwest. Those would be perpendicular to each other, right? But you want 2 that are completely independent of each other. And that's because motion in the plane really does represent 2 independent directions. Motion in this direction and motion in this direction are independent of each other. I can do something independently in this direction and in this direction. To give you an example, let's consider firing a gun from a cannon. What happens in this direction?
It goes really fast.
It goes really fast and it just keeps going. doesn't slow down as long as there's not error. Motion in that direction is just, but what happens in this direction? It falls. If I take two objects, I shoot one out of a cannon that direction, and I drop one at the same time, which one hits the ground first? As long as there's no air resistance, and as long as I'm not shooting far enough that I encounter the curvature of the Earth, right? As long as it's still, that's not important. They will hit the ground at the same time. The motion of vertical motion is independent of horizontal motion. Okay, so it makes use of that physical fact that I'm going to separate these things. I'm going to have choose them to be convenient, whatever you like here. X and Y could be any pair. But I'm going to choose them to be convenient. There are going to be some problems where we're going to want to orient them along a ramp or something, so we're going to choose a coordinate system to match the inclination of a ramp or something else. Okay, so when you're working problems, I expect, if you're going to start, I expect you normally to tell me what your coordinate system is. You're going to tell me your unit vectors, maybe just by drawing them on a picture. And that might be enough. But I want to see some kind of indication of what your coordinate system is. So you're free to choose it to make it convenient. Okay, so now sometimes the vector will be written in as a pair like that. Sometimes, which I don't like a lot. Rizzi does do it in this book, and you can do it, follow it. But when we get to more general coordinate systems, you're not going to be able to write it like that. So you'll see. This doesn't generalize. Now, and to describe any point in the room, I can then have three vectors, three unit vectors, x hat, y hat, z hat, which could be, for example, stand over in the corner here. X hat could be this way, y hat could be that way, z hat could be that way. And then I can put to any point in this room, I can show the displacement vector from there to here can be written as a sum against successive displacements. Now, the order doesn't matter here, does it? Doesn't matter whether I go first along x, second along y, third along z, or mix them up. Vector addition is commutative. God bless. Vector addition is commutative, right? A plus B is B plus A. A minus B is the negative of B minus A. So it's almost the same. It's just opposite sign, right? So because vector addition is commutative, it doesn't matter the order here. I can write it in any order. Just put the z's first, the y's, whatever. It doesn't matter. Okay. So now, given that I could describe two vectors, A, now here's another notation, A sub x, x, plus A sub y, y, plus A sub z, z. So what is that subscript? That indicates the component of A in that direction, how far in A I go, how far along x I go when I go along A, how far along y, and how far along z. So if I tell you to go 30 miles northeast, you're going to go some distance east and some distance north. So the subscript indicates, and it should be below the line, just so you know. It should be way down here. You know, make it way below the line there so it's clear that you're not writing AX. That's different. AX is x multiplied by A. I want a subscript there so that it's very clear that it's... So I don't want that, right? Here, put a red thing around it. No, don't do that. Draw the subscript, make it low. Yes, sir.
So does that mean there'd basically be, like, if you were to break down the A subscript x, there'd be two x's? Because I remember reading about how the A subscript x was the magnitude of A times the unit vector x.
Ah, good. That's the next thing we're going to do here. Okay, so we haven't introduced multiplication yet, so it's coming. It's the very next step. And you just did a multiplication here, so it's the very next step. Okay. So first I want to do addition in Cartesian form. So this is called the Cartesian form of the vector. These things are called the Cartesian form. But I don't want you to think of a vector as primarily a list of three numbers. And that's one thing that if you've gotten introduced to vectors, you may have gotten into the habit of thinking as a vector as a list of three numbers. Right? Vector is what? Something with length and direction, or magnitude and direction more generally. So a vector is not a list of three numbers. Okay? Think of a vector as an arrow. If you want a simple concrete thing. associated with it. Okay, so now suppose we have two vectors in Cartesian form. We have A, in general Cartesian form, some numbers ax, ay, and az, and we have another vector B, and we want to consider what happens if we combine successive displacements. So the vector A plus B is now a third vector, and what we do is simply add the components together. So the Cartesian form makes it really easy to calculate this, the vector sum. If I know the Cartesian form of the two vectors, then I can find the sum very easily. It's really quick. Just add the components. So the reason for using components is to make calculations easier. You'll be able to calculate things in the algebra using Cartesian form. But I want you always to go back to your mind when you're trying to figure things out, back to the basic concept of vector as length and direction, or the mathematical definition of magnitude and direction. Okay, next thing is then multiplication. There's two forms of multiplication that he introduces in this chapter. There's two ways to generalize the concept of multiplication. Remember, what we're doing is to generalize the things that we know in numbers. So we have addition and subtraction. We know how to do that with numbers. Now we're adding directions. So this is how we add, how we combine directions. And now we still have an algebra with things that have directions. So now we're going to do a multiplication. Yes, sir?
I'm pretty sure I understand cross products, but I was totally lost with dot product.
Okay, good. Usually it's the other way around. So there's two names, cross and dot. So there are two forms of multiplication. There's two ways you can generalize the idea of multiplication from numbers. Two ways that you can do this. And the first is that he introduces is called either dot or scalar. And the second way is cross, or also called vector, depending on whatever you like to call it. Okay, so the first one he introduces is dot product. And what is the formal definition of dot product? Where does he describe that? Let's see. Explain the dot product. Where does he first do that? Notice we skipped over, you might have noticed we skipped over polar and spherical coordinates. We'll come back to those. We're going to do this like this. On page 60. Right. Okay. Okay, so he first, in equation 2.7, he defines a dot product of two forms, but he does it in terms of Cartesian, in terms of their Cartesian forms. So A dot B, if A and B are what we've written there, I'm going to take the product of each of the individual components and add them together like that. Okay. Now that doesn't really give you a very physical idea of what dot product is, I think. So he's going to work on that. That's coming next. So this is equation 2.7. 2.8 to me has a more physical explanation of dot product. So A dot B is, he writes it down in several forms. A, B times the cosine of the angle formed by AB, by the two vectors. And then he writes it as AB parallel, or as A parallel B. So let's investigate. It's all the same. All of these are the same. They give the same result. Different ways of understanding it. This is the one I prefer. It seems to me to make the most sense. This is a way of saying, what do these two vectors have in common in the plane? It's a nice way of saying it. So let's consider an example here. How about let's do the following. Let's say one of the vectors is x hat, and the other vector is, so this is A, and B is going to be, let's see, 5x hat plus 6y. Now let's take the dot product between these two vectors. of course, there's 1 implied here. Say it's 1. Okay, that first definition of the dot product will be to write down the product of the x components. So it's 1 times 5 plus the product of the y components. And so, whoops, I'm going to add in here. What are the components along y and z? There are no components along y and z, right? Just to make it clear here. So this is 0 times 6 plus 0 times 0. So this is 5. In terms of the Cartesian components, can you see how it works? Just pair up the Cartesian components, the x components, add them to the product of the y components, add them to the product of the z components. Can you see that? What that means? Yes, sir.
I understood mathematically what was going on.
Right. The
Like
next
the equations helped me understand what it was.
Good. Let's do the next. I mean, he's going to flesh it out here because he's big on your understanding. So the next one here is the one that I think is easier to understand. If we write A, B, okay. How about this? Let me go back a little bit. Let's take some simple steps. Let's do some simple directions first. Let's just do x hat dot x hat. Okay. X hat dot x hat. Looking at it in terms of that the equation that I like here, this one, which I'm going to highlight here. Ooh. No. I was trying to highlight. There we go. Okay. So. Okay. So this is the magnitude of. Sorry, I'm getting used to this thing still. The magnitude of x, the magnitude of x, and the cosine of the angle between x hat and x hat. Right? What's the magnitude of x? It's a unit vector, magnitude 1. So this is 1 times 1. And what's the cosine of what angle? What is x hat? What's the angle of x hat with itself? 0. What's the cosine of 0?
1.
Right. So, what does x hat have in common with x hat? What do these two directions have in common with each other? Everything, which is 1. Now let's suppose we take x hat with the opposite of x hat. X hat dot negative x hat. Okay, so, and cosine of the angle here. What's the angle between x hat and negative x hat? 180, or in terms of radians, it's pi. What's the magnitude of x hat? And what's the magnitude of negative x hat? And what's the cosine of pi? Negative 1. Negative 1. So what do x hat and negative x hat have in common with each other? They're perfectly opposite directions. So viewed as directions, they're opposites to each other. Now, two directions could have some other range of possibilities. What's another possibility? Lots of other possibilities. Two directions could be perpendicular to each other. So let's look at the dot product of two directions. Oops, let's look at x hat dot y hat. What do those two directions have in common with each other? That's like north and east. What do those have in common with each other? Nothing, right? They're independent of each other. So let's look at the dot product between them. What's the magnitude of x hat is 1. The magnitude of y hat is 1. What's the angle between those? Pi over 2. 90 degrees is pi over 2. Cosine of pi over 2. So this is 1 times 1. What's the cosine of pi over 2? 0. So x hat, the dot product of x hat with y hat shows that they have nothing in common with each other. They're not opposites. They're not in the same direction. So two vectors that are in the two directions that are in the same have a dot product which is 1. Two directions that are opposed to each other have a dot product which is negative 1. Two directions that are perpendicular to each other have a dot product of 0. Generally, two directions will have some dot product between negative 1 and 1. Okay? So let's look at that, generalize that to include vectors now. A dot B is the magnitude of A times the magnitude of B times the cosine of the angle between A and B. Right? So what if A is 3x and B is 4y? What is the magnitude of A? What is the magnitude of B? And what is the angle between A and B? Still pi over 2. Right? They're perpendicular still to each other. And what's the cosine of that? 0. So A dot B is still going to be 0. It's going to be 3 times 4 times x dot y hat. And x hat dot y hat is 0, so this is still 0. They're still perpendicular to each other. So the dot product tells you about what do these two vectors have in common in terms of their direction and in some sense magnitude. So it's proportional to their magnitudes, but the big thing is what do they have in common in terms of their direction. So if a dot product is positive, that means the two vectors are kind of in the same direction. If the dot product is negative, that means the two vectors are perpendicular. If dot product is 0. If the dot product is negative, that means these vectors are in opposite directions. So the dot product of 30 miles east with 20 miles northwest, is it going to be positive or negative? Negative. It's going to be negative because east and west are opposites, and the part that's north is independent. Okay, so let's see how this works out here. Let's do this. Let's take x hat dot some vector, some general vector A. Let's take the dot product of some direction with some vector. This is x hat dot A. Now, what I'm not proving to you here is that the dot product is distributive over addition. So I can write this as a distributed product. X hat dot x hat plus a y, x hat dot y hat plus a z, x hat dot z hat. That's using distribution. Distribute the dot product over addition. Okay, now you can see these pieces here. What is x hat dot x hat? It's 1 because x hat's in the same direction as itself. So this is 1. How about x hat dot y hat?
0.
Because? They're perpendicular. They've been chosen to be independent of each other. What is that x hat dot z hat?
0.
For the same reason. So this is then just a sub x. So Mr. Kelly was noting, if I take the dot product of A with the x direction, I get the amount of A in the x direction. That's another way of understanding the dot product.